1.3. So more functions on their graphs. A lot of this stuff is really pretty straightforward. Increasing, decreasing, and then a constant function. Okay? Remember, we always read from left to right. So whenever we look at anything, we're always looking at the graph from left to right, and it's almost like we're dragging a straight line across to see what's happening. The one way that I kind of think about it is if I have a little person here on the graph, what do they have to do to get up to the top? Or if they're at the top, what do they have to do to get to the bottom? Like, where are they going? So in this case, like whenever it's increasing, remember it's just we're walking up the line or up the slope of some sort, and you can have a lot of different graphs that are going to be there we go, that are going to be increasing and then it'll decrease and things of that nature. You know, whenever you're decreasing, basically it's like you're walking down the hill. If it's a constant, then your little guy or little girl, whatever you have here, is just walking across a horizontal plane, okay, or horizontal line. So constant's not going to change. There's not going to be any sort of increase or decrease in your y value from one point to the next. But as you move from left to right, obviously you can tell if it's going up or if it's going down. So then from there, whenever it changes, okay, that's whenever you're going to have different minimums and maximums. Okay, if you remember that from Algebra 2, you have different points on your graph where things kind of change. So like down here, I've got a minimum, and then I have a what's called a local maximum up at the top, kind of the top side of my hill. Okay, it's like I've got a bottom side of the valley and a top side of the hill. So as far as where my graph is going to be decreasing, and then versus where it's going to be increasing. So how many different times would I be basically walking down the hill? Is there 1, 2, or 3 times? There's 2 times that I'm walking down the hill. Okay? So if I think about it, I'm walking down the hill from here to there. Then it goes back up. And then I'm going back down the hill. So the decreasing part is the part obviously in yellow. So where are my x values coming from? Okay, whenever we talk about increasing and decreasing, since those deal with your y values, then we're going to talk about the interval of your x values. So since we talk about the y value in terms of increasing and decreasing, that means it's going to be your x value as far as where your interval comes from. So what's the first interval that I have that's here in yellow that it's decreasing? Where does my x value come from, and then where does it stop? Like, where does it hit and it kind of level out before it goes back up the hill? Whoop. From where? Now, it's continued to keep going, right? So what x value? Negative infinity. So it's going to go from negative infinity. Where's it actually stopping at? What's the x value? 0? It's not going to be inclusive because it's going to be your minimum in this case. Okay, whenever we talk about minimums and maximums, so it's not going to be inclusive because it's at 0, where x is 0. It's not going up or it's not going down. Does that make sense? It's like that lull. That's that low spot, like whenever it hits. So then, if we just continue to roll back through the graph, okay, from in the blue section, what are we doing? We're increasing, right? So what are my x values from where it's increasing? From 0 to where? To 2? Right? Remember, it's going to be broken up as far as my x values. Okay, we always look at it horizontally. So from 0 to 2. Again, I don't include 2 because 2 is going to be a part of my maximum. That's my peak, and it's not increasing there. It's basically getting to there, and it's stopping, and then it's going to fall back off. Okay? So then, the next part, basically everything that's left, is that it's decreasing from 2 to positive infinity. Whenever we look at 2, what's happening and you always remember, we always look at it from left to right. So as I basically go from left to right here, what's happening? Is it increasing, decreasing, or is it constant? It's going to be constant. So it's constant from what's my lowest x value that it's coming from? It's coming from back over this direction, right? It's coming from negative infinity. Where's it going until 0? Now, is 0 included in this case? It is going to be included, okay? Now, here's why is it included, though? What do you notice about right there? It's solid, right? So since it's a closed circle, then 0 is going to be included. So it's constant all the way until it gets to 0, and then what happens? We drop down to the other graph, right? So we drop down to the other graph, and then what is it doing? It's increasing, right? So then we are increasing. Now, in this case, is 0 included? Why not? Because it's an open circle. Okay? So whenever we get to these piecewise functions, especially, we've got to pay attention to, is there a closed circle or is there an open circle? So in this case, there's an open circle, and then it's just going to keep going off to the right, and so it's going to go to positive infinity. Number 3 is pretty similar to number 1 in terms of like where everything's at. You know, like where you kind of have to, where my different windows are, where it's decreasing, and where it is increasing. Okay. Biggest thing with increasing and decreasing is making sure that you always look at it like, if I would start on the far left, am I going to walk up the hill, or am I going to walk down the hill, or am I going to basically walk across that straight line? So then, kind of like what we talked about before, is when we dealt with relative maximum and relative minimums. Okay, I call them local maximums and local minimums. It's the same thing. Local just means that obviously, if a graph is infinite, it's either going to continue to go up or continue to rise, or it's going to continue to fall. So whenever we talk about your relative minimum or your relative maximum or your local minimum or your local maximum, same thing, okay, is that we are going to basically find the low part of the valley and the high part of the mountain or the high point of the hill is really the easiest way to think about it. So relative maximum is an open interval containing a value, okay, such that f of a is greater than f of x, and x can't be equal to a, okay, in that open interval. So, like I says, you know, your local value, basically you're going to use your x and your y points of where's your high point and where's your low point of the graph. Now, again, if it's infinite, if it just keeps rising, then that's why we look at local values. It's basically the one spot where your values go from increasing to decreasing or decreasing to increasing, depending on what you're dealing with. Whenever we talk about odd and even functions, okay, so function's going to be even if we can plug in a negative value, if we can just change the original value of x, but our y values are the same. Okay. Whereas if we plug in a negative value for x, then it's going to change to be a negative value for y. Okay. Every term with an even function, it says the right side of the equation of an even function doesn't change if it's replaced with a negative. So thinking about it, is it symmetrical? Okay, is the easiest way to think about it. If it's an even function, it's going to have symmetry as far as my x and my y value. So like a parabola, okay, is going to be an even function, okay, or at least most of them are. Okay, there are obviously some that don't always fit, okay, depending on what they are, but the majority of the time, if it's an even power, it's going to be an even function. If it's an odd power, it's normally going to be an odd function. Now, again, that can change depending on what we're dealing with, okay, and what kind of graph we have, but that's usually a good way to determine what we have. Okay? The easiest thing to do is just plug and chug numbers just for the fact, like if it's going to be even, odd, or neither. You're going to have a pretty good idea of what's going to happen, but to verify, so like on 4, where it's x squared plus 6, what's your first thought that your even function is going to be? Is it going to be, is it going to be even, odd, or neither, do you think? Even, most likely, right? So we're thinking even. Easy way to do it is try a value that if I plug in, like, what's going to be an easy value to plug in? What do you think? I can't plug in 0 because there's not a negative form of it. So what's the next best number? 1. So if I would go f of 1, and I basically have 1 squared plus 6, I'm going to do the same thing, but I'm going to go negative 1. These two values better be equal. Okay, so I'm going to have negative 1 squared plus 6. So what's 1 plus 6? 7. What's negative 1 squared? Still a positive 1. Plus 6 is 7. So is it even, is it odd, or is it neither? It's even, right? Okay. Now, not telling you it's because of the squared, but that's a good thought process in your problem. Now on 5, where it's 7x to the third minus x, what do you think it probably is going to be? Okay, first thing you want to probably think is odd. Okay, now we still want to take values and again check it to see if that's going to be the case. So if I just go, well, let's make it g because it's g. So g of 1 is going to be 7 times 1 minus 1, 1 to the third, excuse me. So 7 minus 1 is 6. If we do the same thing for negative 1, we get 7 times negative 1 to the third. Now, it's going to be minus a negative 1. So 7 times -1 is going to be -7. Change that to a positive, so +1 is equal to -6. Now, if it's odd, what needs to happen with these two values? They need to be opposite of one another, right? So if I plug in, okay, whatever f of -x is needs to be the opposite of our value. What's your thought process, or what do you think? Huh? Neither? Going with neither? So if I go h of 1, so that's 1 to the 5th plus 1 is 2, right? Whereas if I have h is -1, I have -1 to the 5th plus 1. So -1 plus 1 is 0. What's the problem here? They're not the same and they're not opposite. So I forgot to put that this one was odd. So basically, what do things look like? So what was it? It was 7x to the 3rd, right? And then, was it -x? So if we graph this, okay, it's very symmetrical here. Whereas if we have, is that the right function? Yeah. It's basically like if I can run a line through it, it's going to match, okay? Or at least with it being even and odd, if I run everything through. Whereas if I go to, what was it, x to the 5th plus 1, okay, it looks similar, but whenever we move it with that +1, okay, it's going to change our values and not make everything as nice and neat as we once would like it. Okay, so, you know, like whenever we plugged in the 1 and what do we get? We got 2. Okay, I think my scale's off. But our values aren't going to match to make it to where it's going to be an even or an odd function. So knowing that a function's even or odd tells us the type of symmetry it's going to have. So if it's an even function, it's going to be symmetric to the x or the y-axis, excuse me. So anytime if it moves left, right, if you notice that whenever I run my points for x and y and then -x and -y, it runs through the origin of my graph. Okay? The origin of my symmetry is going to make it odd. Whereas with it even, the y-axis is going to take everything from there to deal with my symmetry. We'll talk about even and odd piecewise functions tomorrow. So that's all you've